Welcome to today's Everon webinar titled Clearing the Air, discussing the topic of air sampling smoke detection, system sample port versus detector sensitivity. Thank you for joining us. We hope this presentation is very informative and educational. If you have any questions for our experts, please click the Q&A button at the top of the screen and select Ask a Question from the drop-down options. We will be answering the submitted questions at the end of this presentation during a Q&A session. I'm going to turn this webinar over now to Ryan Sandler, Vice President of Fire and Life Safety at Everon, to introduce our speakers. Ryan?
Thanks, Brittany. Good morning, everybody, or good afternoon, depending on what part of the world you're dialing in from. Thank you very much for joining the presentation today. I can't tell you how excited I am. I've had the opportunity of working with both Steve and Jeff in the air sampling industry and in the fire alarm industry for many years. So my name is Ryan Sandler, Vice President of Fire and Life Safety for Everon and the National Fire and Life Safety Team. Today presenting, we've got Stephen Joseph and our technical expert Jeff Smith to support us as we go through the presentation today. Stephen Joseph has spent well over 30 years of his career focused on the deployment of advanced detection systems and safety technologies, and currently holds the position for Everon as Director of Advanced Detection and the National Fire Life Safety Team. Throughout his career, Steve has held various positions and duties within the fire alarm industry, many different duties and responsibilities, has taken him across a vast range of industry segments, allowing him to gain exposure in risks and challenges associated with each of those industry segments. His knowledge and expertise and exposure has allowed Stephen the opportunity to uniquely address those challenges and risks associated with each of them, and has allowed him to approach applications from a different perspective, if you will, leading telecommunication providers, semiconductor providers, power generation users, and oil and gas across North America and beyond. Stephen has been instrumental in the development of codes and standards and best practices relative to early warning fire detection, as well as very early warning fire detection, and is very active in our industry trade associations and organizations such as NFPA, SFPE, and AFAA, and others. Joining us today also is Jeff Smith, who for the National Fire Life Safety Team is our technical expert in advanced detection. Jeff has over 35 years of industry experience and knowledge, not just from a installation and technical and application standpoint, but also as a business owner and key stakeholder. Currently today, with the National Fire Life Safety Team, he holds the role as technical expert and specialist for advanced detection, and he works closely with our teams to lead our installation practices, design, and application practices. Jeff is NICET Level 4 certified in fire alarm, and can't be more proud to be part of this team with the National Fire Life Safety Team and working with Jeff and Steve on advanced detection opportunities on a daily basis. So with that, I'll go ahead and kick it over to you, Steve.
Great. Well, thank you for that introduction, Ryan, and welcome everybody, and look forward to the presentation. So with that, as we just get started here, I just want to touch on the importance of advanced detection. Advanced detection and prevention are critical to identifying potential risks to occupants, key stakeholders, and fire responders who may be threatened by carbon monoxide, smoke, heat, environmental gases. So it's really that advanced detection technologies that provide us that automatic indication of something going wrong as early as possible. So as we talk about fire protection goals, always include some level of prevention strategy. Detecting thermal events at the earliest stages of fire development using advanced detection technologies is one such strategy and is imperative in mitigating consequences of fire. So if we can detect early while in the incipient stage of fire development, we have that opportunity to potentially turn what would have been a firefighting event into nothing more than a maintenance effort. And that's really the goal that we set out with respect to fire prevention in conjunction with fire protection strategies. So when appropriately applied, smoke detection plays an essential role in early detection of fires, notifying personnel, occupants, first responders, and initiating sequences at the right time. So for this discussion here, there are 3 common smoke detector technologies, which include aspirating, spot type, and beam type smoke detectors. The selection must consider suitability, taking into account structural, environmental, and notwithstanding performance expectations. So consider issues like temperature, velocity listing, sensitivity capabilities, placement, limitations, and accessibility with respect to environmental, structural elements, and operational challenges. And also consider perhaps the driver for aesthetics or life cycle costs may very well likely be the consideration for the selection criteria of a smoke detector. So fire detection devices must be rated, oriented, and installed in accordance with NFPA 72, their UL listing, and the manufacturer design, installation, and operation manuals. Of the 3 technologies presented, air sampling smoke detection systems have proven to overcome numerous challenges, making it suitable choice across a wide range of applications. So air sampling smoke detectors method of detection relies on a sampling pipe network where sample holes are placed within a fire zone according to prescriptive or performance-based detector placement objectives. A fan, which we may refer to as an aspirator, located in a central detector, pulls air samples from all holes in the sampling pipe network back to a detector chamber where it is sampling and analyzing for particles of combustion. The detection principle is typically light scattering and can best be described as an active versus passive system having multiple programmable levels of alarms across a wide sensitivity window. So considering the technology's operational principle, air sampling type systems can be designed, modeled, and installed to cater for a wide variety and range of application environments, from extremely harsh, dirty, dusty, or polluted to extremely clean, performing where traditional smoke detection systems have always struggled to perform. Air sampling smoke detection systems have become a mainstream detection solution in magnitude of environments across many industries, ranging from extremely harsh, dirty environments, high levels of ambient smoke, such as pulp mills, to ultra clean environments, such as semiconductor clean rooms. This is largely due to the technology's capability to perform and survive in challenging environments, and its ability to set multiple alarm thresholds across a wide range of sensitivity, ranging from also sensitive to very insensitive. So as can be appreciated, every environment will have a unique sensitivity objective considering operational conditions at present and the objectives for the system. So these systems are often relied upon to alert personnel in the incipient stage of fire development. They can also be used to evacuate occupants and dispatch first responders, as well as initiate shutdowns and release suppression systems. As such, alarm thresholds are extremely important when considering a sequence of operation, meaning we don't want to alarm too early or too late for each stage of fire development. We need an alarm at the right time, depending on the condition. So how do we decide where to set alarm thresholds for an air sampling smoke detector? There are sensitivity classifications recognized in codes, standards, and practices. In NFPA markets, these can be summarized as follows: very early warning fire detection, early warning fire detection, and standard fire detection, where spacing, transport time, sensitivity, and air velocity is a function of the classification. So let's focus on these sensitivities classifications. So for very early warning fire detection, alerts are generally in the range of 0.2% obfuscation per foot, and fire threshold is generally in the range of 1% obfuscation per foot. For early warning fire detection, fire is generally in the range of 1.5%, and for standard fire detection, fire is generally in the range of 2 to 4% obfuscation per foot, similar to that of a traditional photoelectric spot type smoke detector. So for alarming, that's pretty clear for traditional spot type smoke detectors where sensitivity is within a fixed range. alarming once reaching its listed sensitivity. What does that mean for an air sampling smoke detector where you have multiple programmable alarm thresholds and the dynamics of dilution? Considering a worst-case scenario, it must be assumed that each hole on the pipe network of an air sampling system will introduce clean air, that is, no smoke, constituting dilution within the detection chamber. As such, for an air sampling smoke detection system, sensitivity is largely based on a function of number of holes and the detector threshold settings. Unless there is only one hole in the system pipework, sensitivity at the hole is different than sensitivity at the detector. To account for this, one must begin by deciding what the target hole sensitivity needs to be for each threshold and divide that number by the total number of holes in the system. Now, this is obviously a function of the manufacturer's flow calculation program, which take other aspects into consideration, such as hole sizes, balance, suction pressure, fan speed, dilution, and so forth. So in this animation I'm showing here on the screen, smoke is shown entering a single sampling hole at the most remote location within the pipe network. The smoke combines with clean air from other holes when it's transported through the pipe, diluting the smoke density. So when the volume of clean air is mixed with smoke-laden air being transported into the detection chamber, the quantity of smoke-laden air is diluted. This dilution effect is directly linked to the sampling hole quantity within the pipe network. The more sampling holes, the greater the volume of air being transported to the air sampling smoke detector. Now, ASD systems overcome dilution by the additive effect that is common to ASD systems. This additive effect is a significant benefit of the technology, which results in extremely sensitive detection system, even when multiple sampling holes are present. During the detection process, air is drawn into all sampling holes in the piping network, which allows each hole to contribute to the total air sample within the sensing chamber. So explained earlier, this is the total volume of air within the detector sensing chamber. The more sampling holes, the greater volume of air. If multiple sample holes are aspirating smoke-laden air, then the smoke particles are combined as they are transported back to the sensing chamber. The ratio of clean air to smoke-laden air is decreased. So it's this added effect that makes the overall detection system more sensitive, say, than a traditional spot type smoke detection system. So for example, let's assume a scenario where the ASD fire level 1 sensitivity is set at 0.1% obscuration per foot. The ASD system is protecting a room, let's say that's 2,000 square feet, and the system is designed with the sampling hole spaced at 14 foot per hole. That's the equivalent of 200 square foot per hole, which generally is considered very early warning fire detection spacing. The resulting detection system would contain 10 sampling holes. So the 0.1% obscuration per foot is the sensitivity of the detection sensing chamber. So to determine the actual sensitivity of the individual sampling hole, multiply the program detector obscuration rate by the total number of sampling holes in the piping network. This is essentially what the modeling programs of ASD systems do. So for this scenario, the detector sensitivity for fire level 1 is set, let's say, to 0.25% obscuration per foot with 10 holes drilled into the piping network. So the corresponding individual sampling hole sensitivity would therefore be 2.5% obscuration per foot. And we'll examine this math, by the way, in more depth in the upcoming slides to help understand how the calculation programs work. So the benefit of ASD systems is active nature to draw into all sampling holes simultaneously. The air is combined in the pipe, transported back to the detector for sampling. When the air is drawn into all 10 sampling holes, the smoke particle concentration increases and the clean air concentration decreases. As the smoke particles are added together, the overall detection system sensitivity is increased. So to explain the additive effect further, take the same 2,000 square foot room with an ASD piping network with 10 sampling holes and smoke particles being drawn into, say, just 2 sampling holes. So to determine the new individual hole sensitivity, the obscuration rating for fire level 1, remember at 0.25% obscuration per foot, is multiplied by the total number of sampling holes, in this case 10. Then we just simply divide that number of the number of holes detecting smoke, so again, just 2 holes, this results in a new effective sampling hole sensitivity of 1.25% obscuration per foot, making the system twice as sensitive as a spot type smoke detector at 2.5%. So you can appreciate how that works then. But to further explain the additive effect, this example can be expanded to include smoke, let's say, entering all 10 sample holes. Each sampling hole would have an individual sensitivity of 0.25% obscuration per foot, making the ASD system 10 times more sensitive than a spot type smoke detector at 2.5% obscuration per foot. So while all this sounds good and positive for an air sampling system, we have to consider, as our codes and standards imply, a worst case scenario as a safety measure. We must assume that potentially only one hole will see smoke, while all others introducing clean air, that is no smoke, constituting dilution within the detection chamber. So much of what we've been discussing thus far is validated by codes and standards that govern ASD systems, such as NFPA 72, Chapter 17. A key takeaway here is that the last paragraph in this document, which states, as part of the system design process, the sensitivity of each sampling port must be calculated in accordance with 17.74622 and 17.74623. So while this language shows up in the annex material, it can be appreciated words such as must and shall is not optional. So air sampling smoke detection systems are engineered systems requiring trained and certified technicians to perform calculations using the manufacturer's listed program, parameters such as detector model, hole sizes, balance, suction pressure, fan speed, dilution, detector model, and so forth are data points used to predict system performance. The output from those programs form part of the submittal for permitting, and they must be transferred to the actual detector during commissioning to achieve the calculated performance. We just can't simply leave a detector at default settings and expect it to achieve intended goals for the system. So it's imperative that we engineer these types of systems to achieve the intended goal for the system. So let's examine a particular manufacturer's calculation program to get a better understanding of hole sensitivity versus detector sensitivity. As defined here, target hole sensitivity is the maximum allowable smoke level at an individual hole with clean air at all other holes that will trigger the detector. Hole sensitivity is the smoke level required at a hole with clean air in all others to produce fire alarm at the specified threshold level associated with the detector. And the alarm threshold is a smoke level at which the detector will report an alarm. So as expressed earlier, calculating hole sensitivity is simple math, but is refined by the manufacturer's calculation program. Let's give it a test. So in this example, I have a detector with a total of 40 holes. My alarm threshold for alert is 0.0093% obscuration per foot times 40 holes gives me 0.372 obscuration per foot at the sampling hole. And we can see from the hole sensitivity table below, we're in the ballpark using this math. I mean, it's refined further with the actual parameters that we discussed earlier, but we're kind of in the ballpark. And we can kind of test that through here. If we look at action at 0.187% obscuration per foot at 40 holes, that's 0.748 obscuration per foot for the alert or for the action level. Fire one, if we're at 0.0232% obscuration per foot, the alarm threshold times the 40 holes, that gives us 0.928% obscuration per foot. Again, fairly close. And fire two at 0.0816% obscuration per foot, 40 holes, that gets us at 3.264% obscuration per foot. Again, the purpose of this exercise here is to show that that simple math kind of translates to more or less what the calculation program is doing, but of course it refines it as we talked about. So if we know the target hole sensitivity we want to achieve, and want to calculate alarm threshold, again, using simple math, alarm threshold is equal to target hole sensitivity divided by the total number of holes on the detector. So once again, assuming 40 holes, let's apply this math, see where we land. So if my target hole sensitivity for alert is 0.4% obscuration per foot, and we divide that by 40 holes, my alarm threshold needs to be at 0.01% obscuration per foot. So again, looking at the math and what the calculation program is doing, I'm fairly close. Let's just look at that across the board here. So action, if my target hole sensitivity is 0.8% obscuration per foot divided by 40 holes, I'm at 0.02 obscuration per foot for my alarm threshold. And fire one at 1% obscuration per foot divided by 40 holes is 0.025% obscuration per foot. And fire two, my target hole sensitivity is 3.5% obscuration per foot divided by 40 holes. That's an alarm threshold setting of 0.0875% obscuration per foot. So the math gets us close, but the calculation program again refines it. So as can be appreciated from our discussions thus far, these are engineered systems with programmable configurations and operational limitations requiring careful attention to specification, design, commissioning, and installation. When appropriately designed, installed, and commissioned, this technology surpasses traditional detection measures, providing unparalleled performance. But if we get it wrong, life safety, asset protection, and business continuity is all at stake. Unfortunately, these systems are often misunderstood or the engineering aspect is underestimated. And too often we find systems inappropriately specified, left at default, randomly set, or not installed in accordance with the design intent and without regard to the operating environment. To appreciate this risk, let's examine some real-life scenarios. So often we find engineer specifications calling out alarm threshold settings, implying detector sensitivity without regard to the actual system design. Depending on the number of holes in the actual design, as we talked about here, this can be dangerous if implemented during commissioning. So this specification example shown on figure one happened to be for a data center where early warning fire detection was the design objective based on 400 square foot spacing and 90-second transport times. Depending on the actual system design and total number of sampling holes, using the threshold setting specified based on 10 holes, we don't meet early warning fire detection objectives. In fact, for fire two, the intended threshold for initiating suppression, we're at 20% obscuration per foot, excessively greater than the threshold listing. Certainly at 20% obscuration per foot, the resulting fire size could be quite catastrophic. So while the manufacturer's calculation program would likely have caught such a mistake, still a commissioning tech using specified thresholds in error would be allowed to enter these set points in the manufacturer's commissioning tool without warning. Hence, this becomes both a specification and commissioning issue, putting the building occupant, assets, and continuity of business at risk. Obviously, this defeats the entire premise of the detection system and the owner's early warning fire detection objectives. Now, using the same set points, consider if the design actually had a total of 30 sampling points on the detector. As you can see here, risk is considerably amplified without warning from the system and no way of catching it during the inspection testing conducted in accordance with NFPA 72, Chapter 14, which essentially just says we've got to test transport of smoke back to the detector and a response at the detector within the allocated time in codes and standards, which for NFPA 72 is 120 seconds. So as you can appreciate here, this clearly puts a facility at risk. So what else could go wrong? Let's consider out-of-box factory default settings. So out-of-box, the detectors come with factory default settings, which include alarm thresholds, time delays, fan speed, pipes in use, relay assignments, airflow tolerances and delays, as well as filter interval timers and so forth. While all settings can present issues if left at default, let's just focus on the alarm thresholds where, in this example, for one manufacturer's product sets alert at 0.025% obscuration per foot, action at 0.044% obscuration per foot, Fire 1 at 0.0625% obscuration per foot, and Fire 2 at 0.625%. So more frequently, we find detectors simply left at default without regard to the actual system design. And depending on the number of holes in the actual design, it's going to be appreciated, this can be quite dangerous. Assuming the system was intended to provide early warning fire detection in an IT environment where early warning fire detection was perhaps the design objective, leaving detector alarm threshold settings at default, do we meet the objective for the system? Well, depending on actual system design and total number of sample holes, leaving the detector alarm thresholds at default values, actual hole sensitivities may be either too sensitive or not sensitive enough. So based on this example of 10 holes, our alert, action, and Fire 1 thresholds, as you can see here, may be too sensitive, resulting in nuisance alarms. For Fire 2, on the other hand, where the threshold may be intended to activate suppression, we've exceeded 4% obscuration per foot and much less sensitive than a traditional spot type detector, perhaps responding too late when needed, and obviously resulting in potentially a catastrophic loss. Now consider the design actually had a total of 40 sampling points on the detector. Risk is considerably amplified without warning from the system and no way of catching it during the inspection testing in accordance with NFPA 72, Chapter 14. So same message here, but much amplified. So really the message is one cannot simply leave a detector at default setting and expect that the system performance achieves the intended goal for the system or be free from false positives. So as can be seen from the examples presented, the net effect of getting it wrong can result in systems being either too sensitive, resulting in nuisance alarms, unnecessary evacuations, false and costly suppression release and disruption, to systems not responding when needed, resulting in extensive fire damage, life safety, and business disruption. So really a lot is at stake, and we need to get it right. So for the specifier and designer of ASD systems, it's imperative to specify the target hole sensitivity required for each alarm threshold as opposed to detector sensitivity. So often I find specifications just simply stating what the alarm threshold needs to be at the detector, maybe even just misunderstanding and applying what they intend to be target hole sensitivities actually specified as alarm thresholds at the detector. So in absence of specification or incorrect specification, we run the risk of arbitrary values being chosen or detectors just left at default. If unclear and you need guidance, consult with technology subject matter experts that understand what target hole sensitivities should be and how to achieve them. So what can be done to ensure you're not at risk? Well, ensure you're contracting trained and certified technicians that understand these engineered technologies. Ensure project specifications clearly stipulate sensitivity objectives at the sample hole, not the detector. And again, if you need assistance determining appropriate sample hole sensitivities based on environment in question, consult with an expert. Conduct surveys of existing installations to confirm systems have been appropriately commissioned or require attention. Simply relying on system calculations can't always be trusted, as system designers often aren't the commissioning technicians. And too often we find that calculations are correct, but the actual program, they're not actually programmed into the system. I would say prioritize surveys where systems are intended on initiating suppression measures, control, shutdown, or have the potential of disrupting the critical infrastructure. So as part of the survey process, it's imperative to also evaluate ambient conditions recorded by the detector over a course of time during the normal operating conditions. So, as I've been touching on achieving target port sensitivities as the goal, we can't always assume that ambient conditions wouldn't warrant some level of adjustment. Understandably, there'll always be some level of adjustment to avoid nuisance alarms, but target hole sensitivity should serve as the basis to adjust from. And of course, once we're done with the survey, the next step is to resolve any deficiencies, ensuring the systems can perform their intended function reliably when needed. And of course, documenting and storing modifications for future reference. So I'm just going to touch on the following case study, demonstrating a real situation and how Everon helped our client navigate through deficiencies and mitigate risk. So a client was a national data center operator. The background is that they rely on air sampling smoke detection for very early warning, with many sites using technology for suppression initiation. So the client experienced some performance issues at one particular site, prompting Everon to conduct a deep dive into the detector settings. Of the detector survey at the site, 100% of the detectors were set at default, where resulting hole sensitivities, as we calculated, were in excess of 40% obscuration per foot for the suppression initiation for fire 2. As you can appreciate, again, that's a heck of a deviation of what was intended for the system. So the action is Everon conducted a subsequent nationwide investigation of priority sites. They prioritized their sites by sites initiating suppression. Of the 11 sites surveyed, 90% of them had either detector set at default or had settings that were inconsistent with the design and sensitivity objectives. I gotta say that the survey process was quite challenging, considering the majority of sites surveyed had missing documentation, complicating obviously the evaluation of the systems in absence of having documents to go off of in terms of the original design. We ultimately had to physically count the number of holes, which, as can be imagined or appreciated, was difficult for pipe networks above ceilings and below raised floors. So the recommendation here is ensure you keep an appropriate record of the system for future evaluation, such as in this case. So the remediation was that Everon reset thresholds according to industry practices, design intent, and owner's objectives for the systems. And as a result, the client feels confident. Once again, their ASD systems are working properly for protection of their data centers. So with that, I'm going to turn this presentation back over to Ryan. Ryan, over to you.
Hey, thanks, Steve. Great presentation, extremely valuable information, very enlightening. And I got to say, from a system integrator standpoint, the case study was quite surprising. It was some information that we suspected, but we would have never imagined in our industry that we would have saw so many detectors left at default settings in an installed application. So pretty enlightening information. Thanks, Steve. So as we talk about what Everon has to deliver to the marketplace and how we support our customers, it's really built on the backs of the National Fire and Life Safety Team, a mechanism or a tool that was really designed and had a vision of being a team that could support our customers and our businesses within Everon itself. And what we've done is we've built a team that can go out and support really all facets of fire and life safety, from fire alarm systems to voice evacuation systems, from mass notification systems to in-building emergency communication radio enhancement systems, to things like we're talking about today, advanced detection, from air sampling smoke detection to gas and flame detection or environmental monitoring. And simply put, we have experts on the team like Jeff Smith, who's joined us here today. He's going to talk about code compliance and installation best practices, applications, and so forth. And really, our vision or our mission within the National Fire Life Safety Team is be able to support the industry, give back by participating in codes and standards and technical committees, but also support our customers and end users as we look at the built environment. Today, flashover occurs at a much greater clip than it ever has before. The challenges and risks associated with the built environment are much greater than the codes and standards are evolving on a 3-year cycle. So really appreciate Steve taking a deep dive into the difference between detector sensitivity and hole sensitivity from a performance perspective. Because really today in the built environment, we really have to go beyond codes and standards and evaluate what are the performance objectives in every application. Next slide, please. And how Everon has done that, a little bit of history here. We came from ADT and the ADT commercial world, and today we just celebrated our 1-year anniversary, but built on the backs of 150-year plus experience in fire and life safety. And we really are looking to be that trusted advisor, partner, and consultant, bringing onto the team industry experts like Steve Joseph, who worked in the air sampling smoke detection world for 20 plus years, and Jeff Smith, who's been deploying air sampling smoke detection for well over 30 years, and bringing industry experts to allow us to be able to look at all facets of life safety, and not just fire and advanced detection, but security, CCTV, access control, and leading our industry to provide solutions and technologies that address new applications as we continue to evolve, from battery energy storage systems to automated storage retrieval systems and warehousing and distribution, to cold storage, and even mission critical settings, as Steve has talked about today, with data centers, telecommunication, and so forth. Next slide, Steve. And how we do that is really built on our legacy business and our transition from ADT to Protection One, the ADT commercial, and Red Hawk Fire and Security, and now today Everon. We have 100 plus locations across the United States, well over 2,500 technicians that are certified, and that continue their education and enhancement in their technical capabilities. Hundreds and hundreds of NICET level 1, 2, 3, and 4. We've got a NICET training technical committee that is responsible for promoting and educating our employees, and challenging them to reach that next level of certification, to continue to grow and serve our base. We have dual 2 UL listed redundant monitoring stations, one in Irving, Texas, and the second one in Wichita, Kansas, to be able to support our monitored customers throughout the United States. And we're just really excited and passionate about giving back to the industry, and hopefully that the information that Steve and Jeff are going to share here today are helpful and in better understanding how air sampling smoke detector systems should be deployed and how they should be considered. I think what we'd like to do as we wrap up here is we left a little bit of time on the back end to have some Q&A sessions. I know that there are some questions out there in the world. The first question, I think I'm going to hand it over to Jeff. Jeff, do you want to talk a little bit about the first question?
Sure. We have a few questions in, actually. So let's first one was, can you provide some quick recommendations for AHJs and third-party inspectors to quickly validate settings in the field? Steve, would you like to?
A great question. And of course, when we inspect these types of systems on an annual basis, again, for NFPA 72, Chapter 14, and as it relates to, what a AHJ is looking for is, sign off that the system has been tested in accordance with the testing requirements of that chapter. which doesn't necessarily require then that the settings be inspected. Now, of course, when you submit your plans on these systems, you're also submitting the calculation programs to the manufacturers, calculation programs that then spell out what the sensitivity thresholds are, what the port sensitivities are, and those form part of the submittal package. And of course, when the system is approved and installed, those get stored away, but when do they resurface? Unfortunately, they don't. And so, as an AHJ, perhaps, concerned about this particular subject, looking to get an output from the detector, specifying what the set points are in relationship to how they were designed and submitted. That's the best advice I can offer in that respect.
All right. Great. Some manufacturers have features to automatically set alarm thresholds based on ambient conditions over a period of time. Since these features don't take into account the number of sampling points, is this a valid way to set the detector sensitivity?
I'm always wary of the auto learn feature. The detectors is a one-time ratcheting effect. It analyzes the ambient conditions over a period of time in which it's programmed to analyze. And when we think about when we commission these systems, oftentimes during the construction chain phase, the facilities perhaps haven't been occupied and perhaps are being learning an environment that is not consistent with how the facility will ultimately operate. Perhaps even a higher level of smoke or ambient conditions that otherwise would be present under normal operating parameters. So unless we're in a clean room and it's a controlled environment, I don't really, honestly, my personal opinion, trust the auto learn feature, and then also consider some of the actions that the system's designed to take, such as the output matrix. If we're initiating suppression, will that auto learn feature adjust the threshold appropriately to be at the standard fire detection and not too sensitive to where we're going to initiate suppression too early? It's that type of thing that you got to be concerned about. So again, caution in terms of use of auto learn features and using them, if you are using them at the right time when it's normal operating parameters, and understanding that you need to ultimately check what those thresholds are and how they relate with respect to output, such as initiation of fan shutdowns or again, suppression initiation.
Great. Wanted to confirm, in slide 13, you talk about the additive effect. This effect would make the detector more sensitive if the smoke's picked up by multiple sampling points. For example, if the smoke is drawn in by 2 sampling points, is the detector twice as sensitive as if only 1 sampling point draws smoke in?
A great question. And back to my example where I used 2 holes. Now, assuming that there was only 2 holes on the system, yes, it'd be twice as sensitive if both holes receive smoke. But in reality, there's generally more than 2 holes on the system, so we have to appreciate that. The other holes have to be taken into the equation to ultimately decide what that sensitivity is going to be, resulting sensitivity is going to be. So of course, this becomes very critical in terms of making sure we have the right set points at the detector, because of that whole premise that if we just leave it at default, if we're not paying attention, the sensitivity could be ultra sensitive, coupled with more than 1 hole seeing smoke. Now we've amplified the situation where the detector could be prone to nuisance alarms. But again, back to what I said, and it's imperative, and this is how our codes and standards appreciate these technologies, is we have to assume worst case scenario, and that only 1 hole will receive smoke. Could be conditions such that only 1 hole sees smoke, and if we're not counting for that, then, and if we just trust that the system's going to collectively see more holes are going to see smoke, so it's a flawed assumption, and presents risk, is what I would say.
Great. We have a comment. The data center example shows the importance of record documents that need to be stored in either hard copy or electronic document format in a document box, such as a space age electronics, air sampling smoke detection system record documents cabinet to store such documents. And that's a good point. If the owners were aware of the importance of those documents, they would certainly want to safeguard those so that in future when the design needs to be evaluated, they would have easy access to those.
100%. And I think you can appreciate having been personally involved in these surveys, the challenge as it related to evaluating the system without the records, and the magnitude of how many sites actually had missing records and what that meant in terms of complication to perform this critical step of surveying the systems, and perhaps the added costs that it implies of having to go under raised floors or above ceilings to find 5/64 holes, small holes in the pipe network that may be hard to locate, or not that accessible. I mean, wouldn't you agree, Jeff, from your past experience?
Oh yeah, yeah. You know, you may know more about the history of it, but it didn't seem earlier on in the installation of air sampling smoke detection systems that this whole issue was either known about or it wasn't, at least from an installation standpoint, it didn't seem like a concern. Is that the case, or was it just ignorance on the installers of this issue?
Well, I think it was multiple of issues. Thinking back to the early days of air sampling smoke detectors, you had to order the detector in the sensitivity range that you wanted. So, typically it was a 0.3% obscuration per foot, for example, 0.03% obscuration per foot. And so, early on, it just got written into standards. If you look at the early stages of NFPA 318 for semiconductor, it actually stated what the alarm threshold needed to be, as without respect to the total number of holes. So it's kind of this disconnect, if you would, in that
Right.
because the manufacturer manufactured a product that had a set sensitivity, that you had to order it, that just translated to specifications, and ultimately then the misunderstanding from an engineer's perspective, and a lot of appreciation for engineers and what they do, but to have a special understanding of to the detail of these types of systems, they're really relying on industry to help guide them. And in absence of that, just specifying or understanding that, all right, there's a target sensitivity, and not realizing that is intended to be the whole sensitivity, not the port sensitivity, often gets people in trouble in terms of actually specifying, detector sensitivity as opposed to sample hole sensitivity. So I think our industry is evolving. The manufacturers are doing a good job in terms of trying to get that out. Certainly, understanding the flow calculation programs and having to define, what your target hole sensitivities are, or having predefined hole sensitivities as it relates to, sensitivity classifications is helpful. But there's that disconnect where the designer is not commissioning the system, and then you have the expertise or perhaps the sophistication of that individual programming the system, commissioning the system, actually transfer that data into the detector.
Sure.
Hey, Jeff and Steve, I love this discussion, and one thing that I think all of us on the call here today are wondering is, as our industry, especially in mission critical, continues to evolve and change, we're seeing a reconfiguration of data centers and telecommunication centers for cooling strategies, for efficiency strategies, for volume expectations, and so forth. what we've uncovered is that in absence of record documentation, it becomes quite challenging to maintain the performance objectives. And as companies acquire companies and there's a consolidation of providers, how much of this discussion is so relevant to today's discussion, and then how much of it is heightened by not understanding the difference between hole sensitivity and detector sensitivity, as that remediation happens and as that reconfiguration happens of data centers today.
Correct. I just say, when I hear that, these systems can't be trusted, they're too sensitive, they're always false alarming. They didn't go off, when we had a fire, and they blame the technology. I think it's the wrong attitude. It's the wrong behavior. We have to understand the systems, if designed appropriately, will perform their intended function. If they're, designed appropriately, installed appropriately, commissioned appropriately, and importantly, just as important, maintained appropriately. So, every time I hear that, these things are false alarming, I immediately think, well, the technician didn't program it appropriately. We need to look at settings, which is exactly what we did in this particular case study that we presented. It was our assumption that that was the case, and lo and behold, every single detector was left at default, regardless of the number of holes. Not the detector's fault, but the fault of actual, expertise of programming the systems accordingly.
Terrific. With that, we're going to hand it back to Corrine and Elizabeth to wrap up the presentation today. Thank you, everybody, for joining. It's a terrific Q&A session and discussion.
Thank you.
Hi, everyone. Just wanted to thank our speakers today. Stephen, excellent job really getting a lot of incredible messaging across. And Ryan, appreciate all of your insights as well. If you do have questions, we encourage y'all to get in touch with Stephen and Ryan. Their information is going to be posted up on the screen right now. And I believe we'll have an email going out after the webinar, which will include those details as well. So again, thank you so much for joining us today, and we look forward to connecting in the future. Thanks, everyone.